Thanks, Sammy. Thanks to the whole AI3SD team for the opportunity to talk today. So I'm going to go through my slides a little bit more quickly than usual, mainly because I made a mistake of preparing for 45 minutes and not giving time for questions. So I'll skim over a few slides, but by all means, ask me questions at the end if anything's not clear. So today I'm going to talk about our work in using machine learning with a focus on causality for solubility predictions in organic solvents in water. So just to give you a rough idea of what I'll talk about, I'll talk very briefly about AI, machine learning, and chemistry. Then move on to causations and interpretability with machine learning models. And then I'll talk about the main chunk of the talk, which is about application to solubility predictions, followed by benchmarking and improvement based on our understanding of the model. So to begin with, I'd like to show you these slides, which is the results of a survey of 151 chemists a few years ago. And this is in this CEN ACS journal here. And what it basically shows is that opinion about machine learning in chemistry is extremely divided. So you've got a large chunk of people agree that it is overhyped, but also a large chunk of people disagree that machine learning is overhyped. And if you look at the content of all the chemists, the different type chemists, and they seem to be quite representative. So what we have with machine learning and chemistry in particular is that we got a trust problem, that people do not necessarily trust machine learning that much. And it comes from this list of problems here. So we got cognitive bias, we got experimental bias, which you've probably heard about a little bit from Eric just in the first talk today. We got spurious correlation, and we got the interpretability problems. And most of these things create a trust problem with machine learning in chemistry and in science in general. So this is my students' favorite example. So if you go to this website, which is called Spurious Correlations, I just managed to hide the link to the website. So you see that again. Anyway, then you see all kind of correlation that makes absolutely no sense whatsoever. So this is the correlation between the divorce rate in men with the per capita consumption of margarines, and you do not expect them to be actually linked together, but you can see the correlation is really, really startling there. And that's one of the problems with blindly applying machine learning, that it will see correlation, but whether that is a causal relationship is a very different story. And so I like to look at something that's a little bit more topical now, because we probably all heard about this study a few months ago from Warwick University that TMO feathers link the eat out to help out scheme to an increase of coronavirus infection rate. Now, the correlation is the easy part. Finding the correlations based on the data is a straightforward part. It's proving the causations relationship, which is a lot more difficult. So what he did was quite clever. He looked at the data windows for the eat out to help out scheme on the day where there is significant rainfall during lunch and dinner time. And in those days, there's a drop in the infection rate that's about 0.03. And then he can compare that to the same values, but on the days with rainfall during lunchtime and dinner time, but 4 weeks prior to the eat out to help out scheme. In those cases, the number is only about -0.02. And so there's a significant change in the drop of the infection rate, the transmission rate, before the eat out to help out scheme and during the eat out to help out scheme, when measured by the impact of the rainfall during lunch and dinner time. And that with that information, then we can have a lot more confidence in saying that there is not just a correlation, this is now a causation relationship between the eat out to help out scheme and the actual spreading of the coronavirus during that period. So I guess what I want to show you from the example is that in other science, people seem to be a lot more careful about the differentiation between correlation and causations, at least in chemistry or in physical science, I think we're still at the very early stage of applying machine learning and AI to our problems, and we are probably a little bit less vigorous in what we do. So with that, I'm going to talk about what we want to contribute in terms of applications of machine learning to our chemical problems. So this is a sort of very simple representation of a regressions model development. You got the training data and you got the validation data. And so you turn the training data into descriptor, which is basically a bunch of numbers that represent your problems. And you feed that into the machine learning method. The machine learning method would use the validation data to optimize, and then at the end you got a model. And this applies to pretty much all regressions models, and probably many other type models as well, but mainly regression model. And once you got the model, then you get the test data, the data you actually want to predict, and you turn that into descriptor, fit it in the models, and it spit out the prediction, which is what you want. And the problems for us who essentially are not computer scientists, not mathematicians, is that we got very little contributions that we can do to the machine learning methods. We can learn how to use them, but we're not really the people who can turn them into better methods. So what we really can do, however, is we can look at this descriptor generation stage. Because for us, this is the critical stage. What we're doing when we turn the training data into descriptor is we're turning our physical, our chemical problems into a numerical problem. And if that translation step is not done based on our scientific understanding, if that translation step is done randomly, then very likely we're going to fit our models with the wrong numbers, and then we lose what we call interpretability. We can't track why it makes that prediction and how much we should trust those predictions. So that's basically our approach. We really want to focus on the descriptor development stage. So to demonstrate that, what we did is we look at the solubility predictions problem. And if you work in medicinal chemistry, if you've got any contact with medicinal chemistry, then you will know that solubility is one of the most important properties to predict for a drug candidate. And so there are two key publications. The first one was in 2008, and the second one is in 2019, and they are called the Solubility Challenge. Now, in the first challenge, AstraZeneca's team and Jonathan Goodman presented a data set of about 100 compounds. 75 is a training set and 25 is the test set, and asked people to make predictions and compare that with the measured experimental values. And no one could make the prediction which are good enough for the job. And so 10 years later, they revisited it by the AstraZeneca team, and they created a second data set which with much higher quality measurements of the experimental data. And as far as I know, we still not be able to meet this second challenge 2 years on with any confidence. So this is a huge problem in medicinal chemistry, but also in organic chemistry in general, because when we look at this, then obviously aqueous solubility is very important for drug design and medical science. But for us, if we look from the synthetic point of view, then solubility in organic solvent is also very important, because it basically dictates the whole process of what solvent you can use in your reactions, how you're going to do your workup and purification to remove all the impurity and to keep the product you want. And so solubility in organic solvent is just about as important when you start thinking about really making compound. And the problems is that none of the prediction methods that doesn't involve experimental data really produce the prediction that we can trust. And also predictions in organic solvents are really rare, because the majority of the effort has been focused on the medicinal approach. And so it's very much focused on aqueous solubility, but organic solvents are much less often visited. So what we set out to do is we want to create a model or a series of models that qualify or satisfy a few criteria that we consider to be important. So we want it to be based on descriptor, which actually represent physical aspect of dissolution processes. We want to be able to rationally improve the model. So it's not just about generating the model, it's about generating the models and go about improving the models based on our understanding of the descriptor and the importance. We want the models to produce prediction as accurate as the training data. So you heard about accuracies of data many times when you work in machine learning. By now is even more important in our particular case, as I've shown you in a few slides. And finally, what we really want is that our model is going to have to reproduce the established physicochemical behavior of the solid solution equilibria. If it does reproduce known physicochemical behaviors of solid solution equilibria, then we can finally trust that the model actually represents reality rather than just random number correlations, because that would give us the confidence to apply it to new compounds that we haven't ever come across before. So the proposed approach is like this. We want to look at the, so I want to move it down here. We want to look at the solutions, the solution behavior phenomenon, and then we divide into solid informations. We got solid-solid interactions. We got solvent interaction, which at least we don't need to represent too much because within the same solvent is self-consistent. But then we have solvent-solid interactions. And so we started putting together physical properties that we believe is directly linked with solubility, and we came up with a number of them here. I don't want to go too deep into this because we don't have a whole lot of time. For the solid state representation, the solid interactions, we use a melting point, and you find out later on how important melting point is or how unimportant melting point is. And then we ignore the solvent-solvent interaction because, as I said, within the same solvent, it should be self-consistent. So the first challenge is data, and I keep hearing about data, but in our case, data is even more a problem because we know we can get tens of thousands of data points with water solubility. It's the organic solvent solubility that we got a problem with. And so we curated the Reaxys database, and we came out with, in the end, about that many data points. These are the most populous solvent in that Reaxys database. So the maximum number of solubility data point we have in ethanol, which is probably the most popular organic solvent in there, is less than 700. And for benzene, we got less. For acetone, we got about 450. And so for that, what's obvious right at the beginning is that we can't do anything fancy like deep neural network or convoluted deep neural network. Those things are completely out of the windows. We got very limited data, and that would have an impact on the number of descriptors we can use. That will have an impact on the kind of models we can use. Now, water is different. There are plenty of data, but for consistency, we came to the Reaxys database, so we end up with about 1,000 data points, 900 data points. And then we come to the next problem. The next problem is that the data is very noisy. So this publication here from John Mitchell, probably quite a few years ago right now, so this is 7 years ago, evaluated the accuracies of the solubility measurements, the experimental data, and came to the conclusion that the log S value that people report is normally wrong by 0.5 to 0.7. If you take the log scale of 0.5 and 0.7, you turn that into absolute number, and the error is actually huge. The error is anywhere between 2 to 4 times easily. And so the values of the solubility is very, very noisy data, and we need to take that into account. The reason why the data is this noisy is normally because either the compound is not pure enough or the solvent is not pure enough, and solvents quite often get contaminated with other solvents, most commonly in moistures, and any of those things can affect the solubility measurement massively. And so once you know that the data is this noisy, then you need to revisit what we call the metrics of model. So normally for all of these, we would use the R-square and the RMSE, the root mean square error, as the metrics of choice because they are reliable. They work across multiple models. They allow you to tell immediately how close your prediction is to the experimental values. The problem is if the experimental value is noisy, then these can be quite misleading. And so we came up with 2 additional metrics. We came up with 2 thresholds. log S within plus or minus 0.7 from the experimental values, and the percentage of predictions of log S within plus or minus 1 to the experimental values. Now, 0.7 is basically the noise in the data. You can't really get better than that. But for the prediction to be useful, then the limit of the errors in the prediction really has to be plus or minus 1. Because if you predict outside that range, then the predictions and the real values is too far apart. You can't really rely on that predictions to make useful judgment on your compound before you even make them. So we got a very narrow threshold to operate with. So just to give you an idea of how it works, this is a plot of experimental solubility versus predicted solubility. And so we create a two threshold here, plus and minus 1 of the experimental log S. So anything falling between these two red lines is basically just about good enough. Anything outside is definitely an outlier, and we need to analyze to see why they are outliers and is there any way we can improve them. So this is how we're going to operate, and those are actually the two metrics I trust more than the R-square and RMSE. So we started with our approach to descriptor, and we got about 22 descriptors. And one of the things that we know immediately is that since we got so little data, we got only a few hundred data points for each of the solvents, we're going to have to cut down our descriptor to the minimum level. So we did the correlation plot for 22 descriptors to each other, and we noticed right away that a number of them are actually correlated to each other. If you look at anything up here in this range of color are basically strongly correlated. So we can remove most of those and just keep one out of each set in order to cut down the number of correlating descriptors. And we can confirm that with our Pca analysis. So if you look at the number of components versus the cumulative variance, and I think that should be R-square actually, to 1, roughly about 14 descriptor is where we got almost complete variance capture, 100% of the variance capture in the data set. So that gives us an idea. If we got about 14 descriptors, it's probably the right number of orthogonal descriptors that we should have. And it turns out if we take away all the cross correlation here, we end up with exactly 14 non-correlated descriptors. So I usually have one slide here with the descriptors, but I removed that to save time. If you really want to see the details of this, obviously you can go to this paper here and have a look at it. But the key things for the orthogonal descriptor is that once you got orthogonal descriptor, the interpretation become extremely easier to carry out. So I did see a question about how do we know how many neural nodes and how many trees and layers we should have. So here's an optimization of the model. So the first one here is an optimization for random forest, and we basically look at the number of trees, and we optimize that versus the RMSE. So you see that RMSE start to flatten now and not decreasing significantly at about 100 trees. And so that's the number of trees we use. And the same goes for the artificial neural network. We carry out the same business, increasing the number of nodes. And when we don't see a significant increase of the metrics anymore, in this case is the percentage within 0.7 and 1, then that's where we stop, because what we don't want is obviously give too many variables into the models and then overfit our data. So cutting the very long story short, this is an example of what we get out of the predictions. So with the water set that is y between log S minus 12 to 2, we see right away that the linear models are basically no good, but that's to be expected. We expect that. We just put them there in as a comparison. But the nonlinear models are actually reasonably good across the board. So the metrics, the two that we are interested in are fairly okay. We got about 80% within plus and minus 1. The R-square is a little bit deceiving, and the RMSE is roughly approaching the errors of the data. But what's really interesting is the standard deviations for the 6 nonlinear method. So if we take the standard deviation for the 6 nonlinear method, they are quite small, except for this one. They're all very small, and that's going to have an impact on what we want to do later. So this is a correlation between predictions between different machine learning methods. So non-linears are all here, and we don't trust them. But the linears are here, and we don't trust them. But the non-linears seems to be quite closely related. The scale is very different now. So we're looking about R squared 0.94. That's how good the correlation between them is. They're very similar predictions. So the method doesn't seem to matter all that much. Just to give you an idea how good the prediction is, this is a Gaussian process prediction for the benzene set. And if we don't count the error bar, now Gaussian process give you the error bars, the confidence in how accurate the prediction is. If we don't count the error bar, we got 80% within plus or minus 7.7, and we got 90% within plus or minus 1. If we cheat and count the whole error bar, then pretty much everything falls inside the range that we want them to be. But the most startling result is this plot here. This is a histogram of the size of the error bar for each of the data, each of the predictions. And you will notice that the majority of the predictions will give you an error bar of plus or minus 0.7, which is exactly what the noise in the data is. So we are really pushing the accuracy of the predictions very close to the noise inherently in the training data. And that gave us a lot of confidence that we are doing the right thing in this case. So the data for ethanol and acetone are not as good. You can tell immediately just looking at the plot. And the reason is because this is the ethanol plot and that's the acetone plot. The acetone plot looks terrible. When we started thinking about it, and actually that makes plenty of sense. Ethanol is regularly contaminated with water, and acetone is worse. It's contaminated with water and it's volatile. And so it's not surprising that the predictions in acetone is worse than in ethanol, and ethanol is worse than in benzene. So far, all these behavior of the models seem to be consistent with what we expect from reality. And one of the things that we went and did that we don't often see other people do with their models is we started looking at the importance of each descriptor. So in this case, on the left-hand side is you see the impact on the two descriptors. So the orange one is plus or minus 0.7, and the blue one is the percentage within plus or minus 1 for the prediction to the experimental values. And the first one here is a full set of 14 descriptors. And then after that, we basically skip one descriptor, whichever one's written here. Okay, so that's the plot. And you notice that with this is water, sorry, this is ethanol. With ethanol, skipping one descriptor doesn't make all that much difference. There's a little bit of movement there, but not much. But with benzene, if you skip the melting point, then your predictions get a lot worse. Yep. And then with the random forest model, they got a built-in feature importance plot, which basically tell you how important the descriptor is. So we did it for ethanol and benzene as well. We thought that was curious. So in ethanol, you got a sort of distribution there. Molecular weight is important, melting point is important. The rest seem to be all roughly important. Looking at benzene is a different story. Melting point is the most important descriptor. In fact, it's overwhelmingly important. So this makes sense because if you think about ethanol, the solvation energy is significantly higher than the solvation energy in benzene. If you think the thermodynamic of the dissolution process, you're basically costing energy to break up the lattice of the crystal structures, and then you compensate with solvation energy. So in benzene, sorry, in ethanol, if the solvation energy is high, then you don't care that much about the lattice energy. But in benzene, you don't have a significant solvation energy at all. All you got is van der Waals interaction and pi interactions. So suddenly the lattice energy becomes extremely important for solubility in benzene. And so that reflects with the melting point. That's so far so good. If we take that and go into the water predictions, again, taking away melting points with water solubility predictions makes no difference whatsoever. And if you look at the feature important plot, in fact, in water, melting point is completely unimportant. And that also makes sense because we know that going from ethanol to water, the solvation energy is going to increase very significantly because water is much better, much more polar, and also much better hydrogen donor to interact with the solute. So in that case, we have a huge increase in solvation energy, and so an extreme decrease in the importance of lattice energy of the organic compound, which tend to be on the small side. So in this case, we don't even need the melting point. In fact, for solubility prediction in water, we took away the melting point completely, and that makes our industrial partner extremely happy because that means they can go and predict for new compound without ever needing any experimental values. So now that we know the solvation energy is important in water, what we've done is we go back to our model and say, we're going to change our solvation model. Now, previously, we used a simple PCM model, which is fairly cheap to do with DFT. But since solvation energy is important, we're going to do the solvation models with something that's a little bit more expensive, more accurate. So we use HF SMD. And the result is quite startling. If you ignore the R-squared and RNA-seq, it just distracts you. Just look at the percentage metrics. You get consistently improvements across the board. Almost every metric is improved by a few percent just by going for a more expensive solvation models and improving our descriptors that way. So we can rationally improve our predictions based on our understanding model and also our understanding of the actual physical phenomena that we're trying to model. So that gives us far more confidence in our predictions that it actually represents reality. So just to give you an idea of how good this thing is after we improve the solvation model, this is a plot for the water solubility predictions. Pretty much nearly everything is inside the red lines. So if we do the benchmarking, and again, this is something I really think every machine learning paper should do, is to benchmark it against the current state of the art. So we benchmark our prediction, which is this one here, against the Aquasol's predictions and the EpiSuite prediction, which are both currently the tool used by the EPA, and you can find it online too. You can do all these predictions yourself if you want to. And we compare it with the Cosmo term prediction tool, which is an ab initio prediction tools that the industry normally would use. And I don't even want to list the metrics here, but it's pretty clear that ours is better in every single case. These are all on the same compounds. If we do that for ethanol, and ethanol is a little bit worse, but in our case, ethanol compared to Cosmo RS, because the EPA tool doesn't do organic solvents, but it's very clear that we're winning by a mile. If we do it in acetone, again, we are significantly better than the current industrial ab initio tools. So just to give you a rough idea how quick the prediction is, it normally takes about less than an hour with the DFT to generate descriptors. Cosmo term typically will take about 6 hours, and we are definitely getting better results in both water and benzene and organic solvents. So the last thing that we did with this is that we validate the tools against real targets. So my student was sponsored by AstraZeneca, so he went to AstraZeneca and he took that data, and I don't ever get to see the structures of this compound. I only see the final results. So there's 191 compounds in water, 26 in ethanol, 19 in methanol. There's far less of them with melting point, but I did say we don't need melting point for water solubility. And so we did the benchmarking. And this is our predictions in water, and this is the Cosmo RS predictions. So it's not as hugely different as before, but still you can see that we have far less under predictions than Cosmo RS. Ethanol is definitely significantly better. So all of our predictions fall within the red lines, whereas Cosmo RS doesn't manage that. In acetone, again, we got a very tight range of prediction here. Cosmo has got it spread out all over the place. So what we did after that is obviously we published a paper, but we also created a solubility prediction tool that is based on our website. So what I'm going to do, I'm going to walk you through how we work with that website. And there's a point to this, so bear with me. So the tool is very simple, and it show you the workflow. We create the Gaussian input file first, and then we use those Gaussian output file based on the calculation with the Gaussian input file to predict solubility. So the first step is to create the Gaussian input file, and I noticed that the structure I put here was completely gone. So I'll show you the structures that we will predict. So we will predict for this compound. This got a melting point of 166, and the experimental value is minus 0.88. Now, just for now, we're going to pretend I managed to draw this structure and keep this here. I click on transfer structure, it give the SMILE string down here. I select the solvent, which is water, and I download the input file. Give me the input file. I go away, run the Gaussians, and get the output file. And I go to the second page and upload the output file for the gas phase, upload the output file for the solution phase, and I select that is DFT, because you can also do this in semi-empirical. You get about 25 times increase in speed. You lose a little bit of accuracy. So I'm going to click the run prediction just to show the machine learning bit, and it should finish in just a few seconds. And it's done, and then I can download the results. So about 10-15 seconds. If I download the results, I will end up with a CSV file. So I'm going to cheat again because I've already got a CSV file. I'm going to show you the output. So this is what's going to be shown in the output. We basically got predictions with different methods. And with Gaussian process, it gives you the threshold. But what's most important here is to look at the individual predictions as minus 1.3, minus 0.8, 1.6, and minus 1. And so the problem here is that these four methods give you different predictions, but if you take the mean, you get minus 0.4, and if you take the median, you get minus 0.88. And that brings us back to this next thing I want to talk about. Minus 0.88 is the experimental values. Now, I do show you that there is correlation, strong correlation between predictions from different methods. Occasionally, one method will predict it wrong, but the rest will get quite close to the correct values. So what we do is, rather than using a single method, we use all four different machine learning methods, and then we take the consensus. So if we do that for each of the data set, then we find out that actually the consensus median and consensus mean tend to improve our accuracy. These are the two metrics that we're interested in. So only these two would be actually what we'll trust. But in every single case, the consensus seems to improve significantly on the single method. So if you take these two values, you get an improvement over there. If you go to benzene set, then there's a huge improvement between the consensus mean and consensus median compared to a single method, and so on. So if we want to sort of hedge our bet and account for the fact that occasionally the machine learning method would predict one value wrong, then a consensus approach tend to sort of even it out and allow us much better metrics across the board. So with that, I'm going to reach the conclusion here and say, at least for this particular study, we managed to tick all the boxes of what we want. We built a descriptor based on the physical aspect of the dissolution process. We did rationally improve the model based on our understanding of the descriptor and the importance. We proved that the prediction is just about as accurate as the training data, and we can reproduce established physical chemical behavior of the solid solutions equilibrium. So we now really trust that this model represents the reality of solubility phenomenon. So we call this causal structural property relationship, mainly with a stress on the word causal, that we really want to establish the causality instead of just simple correlations. And it seemed to produce the sort of model that represent the understanding of solubility model. one of the very important conclusions that we have for ourselves is that it's very clear that machine learning do not replace scientists unless we really understand what we're modeling and we understand all the physical aspects of the properties or the phenomenon we're modeling. Machine learning, blind application machine learning do not give us good result. So with that, I like to thank mainly the person who did most of the work that I present. So Sam is an excellent PhD student, and I thank all of my collaborators in this project at AstraZeneca and INLITS, and I thank you all for your attentions.